Hi, welcome to lecture 2 of the Introduction to Swampland. And Miguel, could you please go ahead?
All right. Well, then thanks very much, Yoshi, for the introduction, and thanks to all of you guys for being back here. I appreciate it. So let me start the lecture. First of all, some of you sent me emails. I didn't have time to reply to those. Sorry about that, but I will get back to those. And I'd like to start the lecture commenting on some points that were left over from previous lecture. So first of all, I promise a reference about finiteness in the string theory landscape and the swampland. So that's this paper here by Heckman and Baffa. So you have the reference there. It's a very nice paper. They point out that there's so this is related to the question of how many effective field theories, you can draw this big blob of the landscape. So this is the blob of the swampland, and I was drawing the landscape as some subset. But really, I should not have drawn it like this. I should have drawn it more like a discrete set of points, because most effective field theories are actually, we expect them there in the swampland and not in the landscape. And this paper quantifies that a little bit. And the way they do so is they say that, for instance, in theories, we believe that, for instance, with theories with, let's say, 16 supercharges, so n equals 4 theories in 4 dimensions, we believe there's just a finite number of couplings we can tune. But there's, in an effective action, there's an infinite tower of higher derivative operators. So you can have, for instance, if you have a Maxwell field, you can have something like the kinetic term of the field squared, but then you can do all sorts of corrections like this form with some energy scale lambda, which is a cutoff. And so in principle, you could have infinitely many theories where these coefficients take different values. They could take any value. And what they point out in this paper is that so what they point out is that all these coefficients, you might, each value of these coefficients, of these infinitely many coefficients, gives you a point here. And so what they point out is there's just like a finite number of coefficients. It's tunable, and all the other coefficients are a function of this. So we believe that just like a very low dimensional subset of the space of field theories is part of the landscape, and the rest of them belong to the swampland. So this is a nice paper that you should look at if you want to learn a bit more about how this is quantified. And then a second question that was asked the other day was, I was asked for examples of theories that were in the landscape versus the swampland, and I gave the example of n equals 4 supergiant mills. We believe is in the landscape. For instance, SUN n equals 4 supergiant mills, we believe is in the landscape only until n equals 23 and not bigger. And somebody asked, could this be related to the fact that the critical dimension of bosonic string is 26? These two numbers seem pretty close. And so I advanced a bit of an argument that this could be the case, and I checked, and it actually works beautifully. So the upper bound on the rank of n equals 4 supergiant mills, you can realize in string theory as coming from heterotic string theory. So in heterotic string theory, you have a worksheet where the half of it is like bosonic string, and the other half is like a superstring. And the gauge sector comes from the half that is like a bosonic string. So the central charge, which essentially is the number of dimensions, has to be 26. Because you have a theory which has 4 non-compact dimensions, you should subtract a 4 here. So the total central charge of internal degrees of freedom has to be 22. And if you have gauge fields, for instance, if you have a gauge field with gauge group G, they give a contribution to the central charge, which is given by this expression, where this is something called the dual Coxeter number of the gauge group. So you can take this general expression and particularize to SUN, where the dimension is n squared minus 1, and you put this level to 1. That's required for simply Lace algebras with 16 supercharges. And you put this this thing to the value that you can find in Wikipedia, and you get this expression that this thing, which is 22, has to be bigger than n minus 1, where n is the n of the SUN n equals 4 supergiant mills. So that automatically gives you n less than 23. So yes, it's directly related to the dimension of bosonic string theory. Okay, so let's keep going. So we were talking about arguments for we're talking about the no global symmetries conjecture. There's no global symmetries in quantum gravity. And we gave like a heuristic argument, which very much relates to black holes, but we also saw its difficulties. And then we got a more rigorous argument in ADCFT using Noether's theorem. So let's keep going. An argument very similar to the ADCFT argument that we just described. Oh, there's a question. Sorry, I have the chat. Let me just open the chat. Can you explain a bit more why the label K is equal to 1? That's very good. So, okay. So this thing is called the level. Okay. So the way you do perturbative string theory, you construct two-dimensional field theory, which is a Worship field theory, and that describes the dynamics of the fields living in the warp volume of the string, and it essentially tells you how it propagates. If you want to have, let's say, SU engaged fields, you need to have a current algebra at level. You need to have a current algebra with the non-abelian symmetry that you're interested. So, for instance, for SU23, I need SU23 current algebra. But then it turns out that even after you specify your gauge group, in terms of specifying current algebras, there's still one more free parameter, which is this level K. Okay, so there's actually not just one conformal field theory that describes SU23 fields. There's an infinite family of them which have K, 1, 2, 3, to whatever. So the K is an integer. In general, you can construct these models with any value of K, and people have constructed those worship models with any value of K. But it seems that when we are studying string theories with 16 supercharges, okay, and you want to have a model which has the central charge 26, it's very difficult, or 22, it's very difficult to get 26 or 22 if you add up fractional numbers. So you need to add up to 22. If you put the level bigger than 1, what happens is that the contribution here is fractional. You need to find another worksheet which has a fractional contribution that compensates this. And typically, you can go through the list of models which would preserve the 16 supercharges. The real constraining thing is the fact that you have 16 supercharges. And for simply laced gauge algebras, there's no known way to complete this 22. Okay, so that's the reason. The reason is supersymmetry and the fact that the worksheet CFTs with theories with 16 supercharges are very, very constrained. Okay. Yeah. Okay. Very good. So since we're talking about perturbative string theory, let's keep talking about it. And now I'm going to mention to you, essentially, it's the same argument we discussed in ADCFT can be used. So this argument very similar to the one that we had in ADCFT shows that there are no global symmetries in perturbative string theory. So we were just discussing how in perturbative string theory, you have a CFT2, which is called the worship CFT. And this encodes the dynamics this CFT encodes the target space dynamics, which has dimension, let's say 10 or 26 in boson. Okay. So perturbative string theory is a bit like holography. You have an auxiliary quantum field theory, is the CFT2, and it encodes the dynamics of the target space. Okay. And it's more or less the same, because if you have a global symmetry, let's say we have a global symmetry here. Okay. Then if it's a perturbative symmetry, a symmetry that you can see in the string worksheet, it means that you also have a global symmetry in the CFT2. And on the CFT2, that's a quantum field theory. You can apply Noether's theorem back to itself, and you get a current J. And this current J You can dress up in a particular way. You can follow the prescriptions in perturbative string theory to construct what is called a vertex operator. So vertex operators are in one-to-one correspondence with physical fields in space-time, corresponding massless to a massless spin one particle. So you recover a gauge boson. So if you start saying I have an exact global symmetry, then what you learn is that symmetry is gauged. Now, this argument is not quite as powerful as the holographic one, because in holography, we believe that the dual CFT sees all the physics of the areas, while in perturbative string theory, we know that the worksheet just sees the physics of some U1s, some gauge fields, not all of them. So there are symmetries that are not captured by this argument, but there are many others what it is. So as I was explaining yesterday, we never have fully general proofs of Swampland conjectures, but you can have partial proofs in very wide contexts. This argument that I just outlined works for any CFT, any worksheet CFT. Okay, and then on top of general arguments, on top of all of this, perturbative string theory, on top of, oops, let me just, yeah. On top of all of these perturbative string theory and ADS-CFT arguments, we have lots of experimental evidence from string compactifications. People have studied string compactifications for 40 years now. They explore wide classes of compactifications. Every single time it looked like there was a global symmetry. People looked a bit more carefully, and there were effects that were breaking the symmetry. Sometimes non-perturbative effects. For instance, there's a string theory which is called type 2B string theory, and in 10 dimensions, it has a scalar field, which is called the Ramon-Ramon action. It's just a scalar field, C0, which seems to have a perturbative symmetry. So if you look at the Lagrangian of the low energy approximation to this string theory, it is invariant under translations of this scalar, under translations of the axiom. And so, you know, that looks like a global symmetry. It's a continuous symmetry of the theory, just translations by the axiom. But this symmetry is actually broken at the non-perturbative level by some quantum effects of instantonic type generated by D-branes. So in string theory, you not only have the fundamental strings, there's also higher and lower dimensional objects that exist in the theory. They're called D-branes. And there's one particular D-brane, the so-called D-1 brane, that generates non-perturbative effects that breaks this symmetry. So this is an example of a symmetry that you don't see in perturbative string theory, but which still is broken by. So this is a symmetry that to which this argument that we were having here doesn't directly apply, but it's still broken by effects that you can show exist in string theory. Okay. Let me give you one more recent outline of recent argument that shows that that there's no global symmetries in gravity, and after that I will take questions about the arguments. So the last argument, so it's most recent argument, so it's gravitational path integral. In a sense, the gravitational path integral recent arguments so there's been a bunch of recent papers on working on these topics, and in a sense, these arguments, they are like the proper rigorous way of doing the black hole heuristic we wanted to do. We now know how to do with a gravitational path integral. So one thing that you can do, it was done in a paper by Ibu Ba, Yiming Chen, and Juan Maldacena, is they consider some scattering amplitude of particles charged under a global symmetry. So remember our charge B that we had. So they have, maybe they have charge under this B. And then they consider a scattering amplitude to, they consider the scattering at very high energies, okay? So they consider 2-to-2 scattering, in which in the intermediate regime, the particles form a black hole, just like what we're doing for the heuristic argument, okay? But they follow the rules of the gravitational path integral carefully. And one thing that we've learned since a few years back is that the gravitational path integral instructs you to sum over all possible topologies that contribute to the scattering amplitude. So this requires a sum over topologies, including some wormhole topologies. And what they show, what they argue in that paper, is that there are there's certain amplitudes like this that lead to violation of global charge conservation. Okay. So there's a concrete calculation that in principle just follows the rules of the gravitational path integral. You still have to buy that, but if you buy that, you get that there's violation of the global charge. And it's actually the formula that these people get is very interesting, because you could say they essentially say that the amplitude that they can compute and leads to the violation of the global symmetry, so amplitude violating, is essentially e to the minus or more like the amplitude square, is e to the minus the entropy of the black hole with mass equals to S, the Mandelstam variable, so the center of mass energy. So S is center of mass energy of scattering experiment. Okay, so they see a very small violation, but there is a violation, and so that's perhaps the latest kind of arguments that you can see in the literature. This paper is from just 2 years ago, that argues in a very general way that there's probably no global symmetry in quantum gravity. I see there's a question: does this mechanism also apply to higher form Ramon fields? Excellent question. I'm not going to answer it right now because it's going to be the topic of what I'm going to be telling you later. Okay. So this is what I'm going to be telling you next. How this no global symmetry applies to higher Ramon fields. I will explain what those are for those of you that don't know. But before I do that, these are sort of like the evidence that we have for the fact that there's no global symmetries in quantum gravity. I think this, it's pretty compelling evidence coming from different avenues. So now we're going to discuss a little bit what the implications of these things are and how to apply it also to higher form fields. But before I do that, I think it's time for questions. Hit me with questions about this. Okay. Oh yes, of course I can provide the reference. Yeah, that's I think an obvious question. Let me just do that real quick. I'm gonna Yes, we actually, while I'm finding this, here it is, I found it. I'm gonna put it in the chat. So there it is. Yeah, this is the paper I mentioned. So since we're talking about this paper, I take the opportunity to advertise. There's a seminar series, a Swampland seminar series that we have on Tuesdays every 2 weeks, and where people discuss papers of interest, recent papers of interest on Swampland. So for instance, we have, if you can look at your YouTube channel, there's a seminar of Juan Maldacena talking about this paper from I think a year ago, or a year and a half. So I think it's a nice seminar series. It's very interactive. You can have every day, you can have like, big shot professors, but also first year students, and everybody interacts together. So you guys are all extremely welcome to come. Yes, I'm gonna put the YouTube channel. Yes, of course you can join. Let me put the webpage for the Swampland seminar. Yeah, so I'm just gonna put the webpage. In the webpage, you can find the link to the YouTube channel and also how to join the mailing list. So that's our website. Okay. So sorry, well, just wanted to. We have a talk precisely about this paper that we were discussing. Okay, so yeah, so there's no global symmetries. That should make us very happy, no? So we are happy. There's no global symmetries. But if we think about it a bit more, maybe we are not so happy. Why? Because look at this result. Okay. So if that is a very small number. So the entropy of a black hole is always bigger than 1. Black holes are very entropic objects. So the exponential of a tiny number is incredibly tiny. Okay. So even though symmetries are always broken, global symmetries are always broken. It might be that the breaking is so small, so as to not be interesting at all. Okay? If you go to a particle physicist friend of yours and tell them, oh, I learned that global symmetries are broken, B minus L is broken, that's great. And they'll be like, oh, that's very interesting. How badly it's broken. You tell them 10 to the minus 100, they will be like, what are you talking about? That is effectively a global symmetry. That's not, that doesn't count. So so that's a real, this is a real difficulty of the no global symmetries conjecture. It's a real weakness it has. Even though it is true that you have learned something about effective field theory just from thinking about quantum gravity, the effect you have learned might be too small. Okay. So there's essentially two ways. Come on again. There's essentially two ways that people have pursued to go around this. Okay, there's essentially two ways that we have pursued to go around this this difficulty. So one, try to find what is the minimal breaking one must always have in quantum gravity. One way you can do that is you can take this formula and you say, well, if it's controlled by black holes and it's something like the entropy of a black hole, maybe is the entropy of a black hole of radius r, where r is the smallest length scale that makes sense in my effective theory. Okay. So if you do that, you get an expression for what is the minimal breaking that depends on your situation. So what does the smallest length scale that makes sense in my effective field theory? How to determine that depends on your theory. Okay. For instance, if so that depends on, that is theory dependent. Okay. So for instance, if your theory has no strings and its behavior at high energy is just essentially general relativity, so you have no stringy states perhaps, and you just produce black holes at some energy scale. That's the case, for instance, in M theory. The smallest length scale would perhaps just be the Planck length. But if you have something like a perturbative string theory, this thing is the string scale. Okay. So string scale is so in string theory, the local physics that appears at long wavelengths at low energies breaks down once you get the string scale. At that point, you need to use worldsheet and all the other story of string perturbation theory to understand the dynamics of the theory. So so it's theory dependent. But taking into account this theory dependence, applying this formula to different contexts seems to give results which are in agreement with the symmetry breaking effects that one finds explicitly in string theory compactifications. Okay. So that's probably the smallest breaking there is, and it's very tiny. So perhaps not the most interesting thing by itself. The next thing that one can do, and now things get more interesting, is apply ideas of no global symmetries to the kind of thing that that Pavitra was talking about. You apply ideas of no global symmetries to higher form symmetries. Okay. So now I'm gonna tell you, one, what is a higher form symmetry? And two, what does it mean to break them? Okay. If you're gonna be working in the more formal side of high energy physics, higher form symmetries are a concept that entered the field in, they had been there already in one form or another, but really the field that introduced them is a paper by Gaiotto, Kapustin, Seiberg, and Willett from 2014. Okay. And they have become a standard part of the language. So it's something that really is important that one learns. So to understand what a higher form symmetry is, let me start with the stuff that you already know. So higher form symmetries, or also called p-form symmetries, where p is any integer, any positive integer. So these P4 symmetries are a generalization of the usual concept of the usual concept of symmetry, where charged objects are not particles. Okay, in an ordinary symmetry, we understand. So a symmetry, as we were discussing yesterday, leads to a conserved charge, and that conserved charge in an ordinary symmetry is carried by particles. Okay, so you have a particle with you know, like we were discussing yesterday, a particle with variant number 1. Okay, so what does that mean? That means there's an object which cannot disappear. The charge cannot disappear, but the charge is localized on a word line of a particle. So in a higher form symmetry, it's exactly the same idea. It's just that the objects that are charged in the symmetry are not particles, but they are higher dimensional objects. Like strings, you know, a string, membranes, so a 2-dimensional surface. Or if your theory, if you're in 4 dimensions, you can have particles, strings, and membranes. There's no room for you to get more objects. But if you're in, let's say, in 10 dimensions, that is often the case in string theory, you can have even higher dimensional word volumes. You can have, instead of a membrane, you can have what we call a 3-brane, which has 3 dimensions of space and 1 of time, or a 4-brane, or a 5-brane, you know? So more generally, or higher dimensional, extended objects. Okay. So it's a string, membrane, yeah, whatever else. Okay. So that's why they're called higher form symmetries, because the objects that are charged under them, they're higher dimension. Just like the physical content of having an ordinary symmetry, so ordinary symmetry, which in the language of high form symmetries corresponds to 0 form. So I told you can have P form symmetries for any P. P equals 0 corresponds to the case that you're familiar with. So it's one particular case. So what happens is that you have the statement that you have a 0 form symmetry, or you have an ordinary symmetry, is that there are particles in your theory whose word line is unbreakable. You have this particle, and the particle cannot just disappear. Okay. If the word line of the particle, you know, if there was a quantum process by which this particle could just disappear, that would mean that the symmetry is broken, because the charge is not conserved. So there is a conserved charge. So that you could say there's a conserved charge. And semi-classically, you can understand is as just the number of particles with charge. So if you have a configuration with, you know, several word lines of particles, you could just count, you put a spatial surface, you count how many times the word lines of the charged particles intersect the surface, and that is essentially what the charge operator we were constructing yesterday is doing for you. Okay, so that's an ordinary 0 form symmetry. This is the usual description or semi-classical description of what a ordinary symmetry is. I am now going to describe how the picture changes for higher form symmetries. But before I do so, any questions? Okay, I'm gonna start drawing while you think of questions, but I'm gonna shut up in case you have some. Okay, So now that we understand zero-form symmetry, let's understand qualitatively how the next case works. That's the one-form symmetry. And in one-form symmetry, instead of the charge states being particles, the charge states are strings, okay? So they are extended one-dimensional objects. So if I draw time like this, and this is a space, these two are space coordinates, you see here the word, what is called the wordsheet of two strings. So it has one direction of space and one direction of time. And you know, the idea, okay, is that because there is a symmetry, in the same way that for ordinary symmetries, what that means is that the word line of a particle cannot end. What it means for one-form symmetry is that you have a one-form symmetry is that you have strings in your theory. So you have strings whose wordsheet cannot end, okay? So for instance, a process, you know, you could imagine that you have a process like this, okay? So where you have the string wordsheet and then perhaps some sort of hole nucleates, okay? And if a hole nucleates, then a configuration like this is also possible. So you could have a configuration like this, okay? So if you have a configuration like this, for instance, if you put, maybe I want, let me just redraw this. If a hole can open, then you can have a configuration where this is time and this is the wordsheet of the string. And if a hole can open in the wordsheet of the string, the hole could be like this. And so what that means is that here at t equals 0, you have a string, and here at t equals 1, you have no string. So the string has disappeared. That's an example of a theory. You know, if something like this happens, that would mean there's, in this case, there would be no one-form symmetry. And if processes like this are not allowed, then there is a one-form symmetry, okay? Oops, sorry. And you know, in the same way that here you measure the charge with spatial integral, you can also construct charge operators that essentially they are wrapped around, you know, transversely to the word volumes of the strings, and they count how many strings are intersecting some surface. So you can also construct symmetry operators or charge operators that measure how many strings are there in a given configuration, okay? So that is a bit too abstract, okay? And certainly, you know, with drawings, you don't get a quantitative handle of what the one-form symmetry is. Okay, so let's just describe all of this with a bit with operators. Okay, so let's talk about what is the operator language for this. You know, for a zero-form symmetry, you have a conserved current, okay, which is this one form J mu. That's the current that you get from Noether's theorem. And you also get charge operators. And charge operators, what they do, if you remember, they create particles, okay? So if you, by hand, introduce a charge operator in the theory, it spits out a word line of charge particle. Okay, the charge operators, phi of x, they're local operators. They create particles charged under the symmetry. So for a p-form symmetry, you have, instead of a one-form conserved current, you still have a tensor, which is totally antisymmetric. And it has p+1 indices. And then the charge operator, you know, because, you know, a local operator spits out a particle. The charge operator, in this case, has dimension P. So it lives in some subspace of dimension P, so that if you have a charge operator, let's say, which is like a line, it can create the word line of a particle. So if this is my charge operator, then it creates, for instance, in this case, here's a line operator, creates a string, and so on and so forth. Okay. Okay. So to give you a very concrete example of a theory with higher form symmetries, let me give you one concrete example. So example of theory with higher form symmetries. You have, it's a theory you all know and are familiar with. It's Maxwell theory. So this is the theory of just, you know, a massless U1 gauge field. This, what I'm gonna tell you, works in any number of dimensions, but just for concreteness, let's do it in 4 dimensions. Okay. And so the fundamental degree of freedom of this theory is the vector potential, A mu. And you have equations of motion within differential form notation. They're written like this. This is one of Maxwell's equations. And then there's another one, which is just the absence of magnetic monopoles. So this is called the Bianchi identity. But it really is just one other of the Maxwell's equations. It's just in ordinary notation is this one. Okay. Yeah, very good. So you have these 2 theories. Okay. And if you think about the about this object, this F is a 2 form. So that means it's really an index to tensor F mu nu dx mu wedge dx nu. So that means it's a 2 index antisymmetric tensor. And indeed, these 2 conditions, here and here, are conservation equations. Okay. So the first equation takes the form E mu F mu nu equals 0 in ordinary notation. And the second one is d mu epsilon mu nu rho sigma F rho sigma, where this is the antisymmetric tensor, equals 0. So they look like conservation conditions for an object with 2 indices. Okay. So if I take J mu nu equals to F mu nu, then this is telling me that I have an object with 2 indices. So a P form with P plus 1 indices and P plus 1 is equal to 2 means that P is equal to 1. So I have a 1 form symmetry. Okay. And here I have a different object, J mu nu tilde, which also has 2 indices. So I have another 1 form symmetry. So free Maxwell theory has 2 1 form symmetries with currents J mu nu equals F mu nu and J mu nu tilde equals to epsilon mu nu rho sigma f rho sigma. Okay. So if I go back to my table, having a one-form symmetry means you have a current, but it also means that you have charge operators. The charge operators under these two symmetries are, they have to be, if I look here, they have to be dimension 1 operators. So they have to be operators of the gauge theory that live not on points, but on lines. And in fact, there's a very natural kind of operator that people discuss, which behaves like this, which is called the Wilson line. Okay. So what you do is you pick a closed loop L in space-time. So okay, that was not a great drawing. So you pick some loop L in space, L, okay? And then you construct an operator, which is just take A of X, so A mu, the X mu, A mu, the gauge field at each point, and integrate over the line. And that gives you a line operator. In any gauge theory, the operator should be gauge invariant. And you can check that this one is invariant under gauge transformations. Because gauge transformation sends A mu to A mu plus derivative of some gauge parameter lambda. And because the loop is closed, the integral of d mu lambda dx mu is equal to 0 on a closed loop. So this operator is gauge invariant and is actually charged under this symmetry. The operator's charged under, so this operator is called, by the way, a Wilson line. There are very famous operators in the study of gauge theory. The operator, this other operator, the one that you get coupled to this current, you can obtain by dualizing the photon. So in 4 dimensions, vector under electric magnetic duality becomes a vector, some other vector v. And so you can consider the Wilson line of the magnetic vector. And that's the operator charged under B. This other operator is called the Toff line. Okay. So Maxwell theory has one-form symmetries with these two currents, okay, and these two charge operators. Okay. So what that means is that okay, so this was a general, I see there's a question, let me finish this and I'll address the question. So what is the point of all this discussion in the context of no global symmetries in the Swampland? Well, so we have learned, oh, come on. We have learned that Maxwell theory has one-form symmetries. So now imagine you have Maxwell coupled to gravity, to quantum gravity. There are no global symmetries in gravity. And all the arguments that we were discussing before apply in this case. So the symmetries have to be broken. So these symmetries have to be broken. And now comes the really interesting thing, which is that And here, so this is where all the discussion about higher form symmetries pays off, which is, to break zero form symmetries, to break ordinary symmetries, we just add terms in the Lagrangian and break the symmetry. To break higher form symmetries, you cannot do that. You need to break them, we must add new particles, new objects in general to the theory. So no global symmetries predicts new states. And this is why applying no global symmetry to higher form symmetries is very powerful. So what I'm gonna do next is I'm gonna explain why adding new particles breaks the one form symmetry in the Maxwell example, and then I'm gonna explain what you get out of that in string theory. But before that, let me address the questions. So Maxwell theory is a good example. A question not correct is the Salam problem. A new Maxwell theory is conformal field theory. And 5 dimensions higher Maxwell theory are not conformal. Are the extra one form symmetries anything related to conformality? Well, from the point of view of the discussion that I'm doing, there's really no difference. For instance, Maxwell theory has an electric one form symmetry and a magnetic D-3 form global symmetry in any number of dimensions. In spite of the fact of the correct fact that you're mentioning that in 4 dimensions, the Maxwell theory has a dimensionless coupling and it's a free theory for any value of the coupling. So you could say it's a free conformal free theory. And in higher dimensions and more, it's not. There is some connection. There's some papers by Clay Cordova and friends where they argue that certain kinds of higher form symmetries, for instance, cannot be realized by CFTs. Okay. So in that sense, there might be an indirect connection. But to look that into more detail, one will have to look at exactly what is the constraints they have. They have them mostly, I think, in 6 dimensions. There might be something in 5 dimensions. I don't remember right now what the constraints are. But if you were to look at those papers, you might find a connection between conformality and higher form symmetries, which is what you're asking about. Okay, so can you repeat how to get V out of A? I cannot repeat what I didn't explain properly. Apologies about that. I just didn't give you the details. So let me do that. Okay. So how to get the V from the A is an example. I'm gonna put it down here. So I'm gonna put down here. It's an example I'm gonna do now. It's an example of electric magnetic duality. If you want to learn about this, I recommend a paper, it's in lecture notes online, which is by Jose Figueroa O'Farrell. Maybe 1 hour or 2 hours, I don't remember, which is called Electromagnetic Duality. The paper is called Electromagnetic Duality for Children. Okay, so he explains all of this very well. But what is the basic idea? The basic idea is that whenever you have field theories, okay, the fields that you have, like for instance, the A, is just some variables that you use to describe the dynamics. But just like you can describe a problem in Cartesian coordinates or in polar coordinates, you can choose one set of fields to describe a problem or a different set of fields. In the particular case of Maxwell theory in 4 dimensions, okay, what we have, let me use differential form notation. You have one form A, which satisfies these 2 equations. So this Bianchi identity and d H star F equals 0. If you're not familiar with higher form symmetries, it's just a different way of rewriting these 2 equations. The 2 equations that I was writing here before with less indices. So it saves me time. Okay. So you have these 2 equations. And if you think about it, this is an object with 2 indices. And in 4 dimensions, this is also an object with 2 indices because this is like epsilon mu nu rho sigma F rho sigma. This has two indices, they're contracted with these two, so it's also an antisymmetric tensor with two indices. So there's a certain symmetry to the equations. So it turns out the one thing that you can actually do is you can say, you know what, I am gonna define a new field strength, I'm gonna call it G, and it's just gonna be the Hodge dual of F. And then I can just rewrite these equations in terms of the new variables. And so the first equation becomes the Hodge star of G equals 0, and D G equals 0. And the star is related to the epsilon tensor. It disappears because the epsilon tensor squares to 1. So you get these new equations. They look exactly as the old equations, but for a different thing, which is called the G. So just like you know that the F is equal to dA, this equation actually, by something called the Poincare lemma in mathematics, means that G is actually D of some other vector. But it's not the same vector because G is not exactly the same as F. It's like different, it's a change of variables, so it's not exactly the same. So if you want to say that G is the derivative of some vector, you should not call it A because that would be repeating the variable. You should call something else B. Okay? So it turns out, as you can see here, that you can write the Maxwell system either in this way, using F and A as your variables, or in this other way, using G and V as your variables, okay? So that doing this change of variables, I just did it here at the level of the classical equations of motion of a free theory. The cool thing is that you can do it. It's really very, very cool. I really recommend you have a look at this. You can do it for interacting theories at the quantum level, and sometimes doing this kind of transformations, which we call dualities, is the kind of thing that gives you the strongest handle on quantum field theory, oftentimes, particularly in supersymmetric quantum field theory. So this is an example of electric magnetic duality. And once you have this variable V, you can rewrite the same operator you had here, the Wilson line. You can do the Wilson line for the other guy, and that's called the top line. Okay, good. So there was another question. Let me see. Excellent question. Can the higher-form symmetry be broken by adding mass terms in the Lagrangian? No, it cannot. Okay, that is very, very important. So why not? Let's try to understand a bit more why not. So let's say this is the Lagrangian for the free Maxwell theory that we have, 1/4 F squared. Now, Pavitra is asking, can we add a mass term? That's gonna change the theory. It's gonna make all the fields massive. Maybe destroys the symmetry, just like adding a mass term to a massless scalar destroys the symmetry. Well, the thing is that we cannot add this thing. It's not gauge invariant. This is a Maxwell theory. It has a gauge invariant. A goes to A plus D lambda. No way. You can forget about this. I'm sorry. No. You could, if you had an extra scalar, do something like a Higgs mechanism, and then you can add a mass term. But that's not the theory we're talking about. The theory we're talking about doesn't have that. Okay? So you cannot. You might ask, okay, fine, I cannot add this thing. Could I add, like this kind of operators I was mentioning, could I add F to the N, whatever, lambda to whatever? That's going to change the equations of motion. So for instance, the equation of motion is no longer going to be Hodge star of F equals 0, but it's going to be Hodge star of F plus F to the N minus 1, very schematically, F lambda and minus 2 actually, 0. So adding higher derivative terms changes the form of the current, but it doesn't change the fact that there is a conserved current, and the form for the Wilson loops, the charge operators are exactly the same. The Wilson loops here, they are very much fixed by these guys. They're very much fixed by gauge invariant. There's no way you're gonna change that just by doing stuff. So no. So actually, you cannot break higher form symmetries. This is another thing. I'm gonna write it down because it's so important. You cannot break higher form symmetries by adding Lagrangian terms. Now, this is a very important point, and I just explored two possibilities that didn't work. You could wonder, could there be any others? The reason why, the deep reason why it doesn't work is because high-form symmetries are non-local, and everything you write in the Lagrangian is a local term. There's a very nice review, I think by John McGreevy, where he discusses this point. It's a review on high-form symmetries. So I don't think I should look for it now because it would take me a while, but I'm gonna make a note. For the next lecture, I'll have the review for you. Okay, good. Very good. Yeah, I think so. I think these were all the questions. So I know we're supposed to take a break at 1 hour time, but I am this close to getting to the nice statement. So I'm just gonna give you the nice statement, and then we make the break, and then we just go on for another 50 minutes or 45. Is that okay? Okay, perfect. So thank you so much again for the questions, really, guys. This is great. Please keep it up. So there's no global symmetries in quantum gravity. Maxwell theory has one for symmetries. So what does it mean that we break them? If we cannot break them with Lagrangian terms, how do we break them? Well, remember, I told you that breaking a higher form symmetry, imagine I have a 1 form symmetry. So I have the word line of my string. So having a higher form symmetry, you know, I drew it, I should draw it like this. Like if there's an actual higher form symmetry, this thing goes on forever. Breaking the higher form symmetry means that the word line of the charged objects can end. Breaking a 0 form symmetry means that the word line of charged particles can end. Breaking the 1 form symmetry means that the word line of strings can end. So there can be, you know, regions or effects where a string ends like that. Okay? But if a theory is Lorentz invariant, okay, if a theory is Lorentz invariant, and I am allowing myself to say that there's like space-like boundaries where the string can end, it also means that I can construct the boundaries like this. You know, why not? Just like that. So what that means, okay, when you look at it at constant time, at t equals 0, so this time slice, for instance, what this means is that, for instance, breaking 1 form symmetry means the strings can open. Okay, so you have a string like this, and there is an allowed process that, you know, allows the string to break, and it gets some endpoints. Oh, sorry, it gets some endpoints. Then this is a theory which has an approximate 1 form symmetry where the symmetry is broken. Okay, and now let's apply this idea to the Maxwell theory. Well, in the Maxwell theory, we were talking not so much about the charged objects, the strings. They are electric flux tubes, those strings, by the way. We're talking about the charge operators, the Wilson lines, right? This kind of guy. You would do it. So the picture is you put the Wilson line in some loop L, and so this is an operator that creates a string worksheet like this. This is time. If my theory has strings that can break, so I can put, let's say, a boundary on a string like this, I could take the boundary all the way to the charge operator. And what I learned is that also the charge operator can end. So breaking 1 form symmetry means strings that can open, and again, breaking 1 form symmetry means charge operators can break. So these Wilson lines can break. And now I'm getting to the punchline. What does it mean that a Wilson line can break? Well, what that means is that there should be a way to make a gauge invariant operator. Oh, this is starting to go bad. Operator where L is an open line. Okay, so if I have, I usually integrate the reason why Wilson line is gauge invariant is because if I have a closed line, okay, so I have a closed line here, then when I do a gauge transformation, this changes by A plus D lambda, and so this is the same as A plus integral of D lambda, okay, but this is by the mean value, sorry, by the Stokes theorem, this is just lambda of endpoint. For instance, if you parameterize it as a circle with some angular data, this is the curve L. So this is lambda of 2 pi minus lambda of 0. But for a closed curve, 2 pi and 0 are the same point. So this is 0, so the thing is gauge invariant. If instead you have an open line, then when you do the same transformation, this becomes, so this is point P2 and point P1. This is lambda of P2 minus lambda of P1, which is not gauge invariant. Gauge invariant means that whatever gauge transformations you do, I get to choose my lambda of P1 and P2, whoever I like. It's not invariant. However, there is a cool way to fix this. We were talking about the free Maxwell theory. Free Maxwell theory, we're writing these equations of motion. It's a theory which has no charged particles. The other thing that we like to do in Maxwell theory is to add charged particles. We add it as a current here. Okay, so if I add charged particles, that means I also have, so if you add charged particles to the theory, this also means that you also have, for instance, you have a charged particle, let's say it's a scalar field and we call it phi. That means you get operators like phi of x that create charged particles. And these operators are not gauge invariant because under a gauge transformation, they transform as usual. This operator of charge Q transforms like this, right? This is the textbook gauge transformation of a field of charge Q that you guys have learned in the undergrad. So this is not gauge invariant. It's not a well-defined operator. But look what I can do. Suppose I construct an operator which is like a Wilson line. And the Wilson line is inserted in some curve that comes from outside of the screen and ends at some point P. Okay, so as we just discussed here, this is not gauge invariant. But I then multiply with psi of minus Q, operator of charge minus Q, localized at point P. Then when I do a gauge transformation, the first factor picks a phase e to the I Q lambda of P coming from this term. Remember, the Wilson line is the exponential of this, so you need to exponentiate. And this guy gets another phase, which is e to the minus I Q lambda of P. So two wrongs make us right. And we learned that this operator, which is the product of the Wilson line and a charge operator, is gauge invariant. So to break the one-form symmetry, we need to have Wilson lines that can end, and we can only have Wilson lines that end if we have charge operators. So we learned that breaking one-form symmetry of Maxwell implies, so imposing no global symmetries implies existence of electrically charged particles. Okay, so breaking hydroform symmetries forces you to have charged states in a quantum theory of gravity coupled to a theory with hydroform symmetries. As a quantum field theory, free Maxwell is a perfectly fine theory. In fact, as it was pointed out in the questions, it's even a conformal field theory. It's the nicest kind of theory. It's a free conformal field theory. When you couple it to gravity, you must have charged particles, okay? And in fact, you know, the Wilson line has some parameter here, Q, which is a charge. It's like the charge of the electric field. So this has to be true for Q equals 1, 2, 3, for all charges. So you must have electrically charged states in all possible charges, okay? Maxwell also had another symmetry, the one that came from the V, the magnetic one from symmetry. And the objects that you need to introduce to, so for the magnetic symmetry, the objects that you need to introduce to break them are magnetic monopoles. And again, you have magnetic monopoles of charge 1, 2, for all Wilson lines, okay? Now, this is something extremely interesting even for our own universe. In our own universe, there's electromagnetism. We have a Maxwell theory, and we know there's electrons, but nobody has ever found that if there's a monopole, okay? We've never found a monopole particle. We've looked for them. We haven't found them yet. So that if they exist, they must be very rare. But this is making a prediction that magnetic monopole particles must exist just from the fact they're coupled to gravity, okay? Which you wouldn't know otherwise. So that's another prediction of the no global symmetry conjecture, the existence of magnetic monopoles of all possible charges. And just to give the statement and then answer questions and we're gonna break, the idea that breaking all High-Form symmetries leads you to, so the idea is that breaking High-Form symmetries means that every possible charge that can be realized in the theory is realized by a physical particle. So this is called, it's a very important consequence of no global symmetries. It's called the completeness principle. Completeness principle. Okay, the idea is that every theory of gravity has all possible charges. So any consistent quantum gravity has a complete set of charge states. Okay, it's a very powerful principle and it comes from no global symmetries. So what we'll do next is to show you how this completeness principle can be used in string theory. It has been used recently to recover the existence of some objects that we knew existed and to predict new objects. And then we'll move on. But before I do that, let me answer the questions. Is there any particular mathematical form of the charge operator phi of GP which stresses the Wilson line? Not in general. Depending on your particular theory, you know, this might be a composite operator you construct in terms of other operators. The only thing I'm saying is that, let me be very concrete. The only thing I'm saying is that I started with the Maxwell theory. Well, okay, I wrote the Lagrangian somewhere, but I don't find it. So I start with the Maxwell theory, which has this Lagrangian, right? This theory has a 1-form symmetry, so it's not compatible with gravity. So to fix that, I modified by adding a scalar field of charge Q. So that's like a scalar field, which is coupled like in the usual way. Okay, so I literally just added a fundamental charge field. This one could have a mass if you like, okay? So this doesn't have to be light, okay? So you could have a mass term. But once you have the charge operator, you can do this dressing like this. So in this particular case, it was just a fundamental field I added to the theory, but it, depending on your theory, could have any other form. Any field, local field that you can construct that has charge Q under the gauge symmetry will do the trick. So the general answer depends on the theory. Any more questions about the idea of completeness principle? Okay. I'm gonna show you now how it works in string theory. But the basic idea, I mean, the fact that you predict magnetic monopoles in our universe is pretty cool. Like when I was in the undergrad, I remember when you study Maxwell's equations, you see the divergence of B is 0. And I remember talking with my mates at the time, like, well, could you make it non-zero? And would that be, do we know for sure that's the case? If you believe there's no global symmetries in quantum gravity, then it has to be the case, which is, I think, a very important piece of information I wanted to highlight. Questions? Okay, so here we are, the completeness principle. Any consistent quantum gravity must have a complete set of charge states. And this is very powerful. So my iPad's starting to slow down, but I know the trick by now, which is to open a new note. So I just did that. So let's now see what the completeness principle can do for you. So let's see if this is true, this completeness principle thing is true in string theory. Okay. So to do that, I need to tell you a little bit about string theory first. And we'll study just this. There's 5 string theories in 10 dimensions. We'll study 2 of them, which you can study sort of like in a unified way. So in 10 dimensions, so there's the 5. Okay. So there's 5 string theories in 10 dimensions. Okay, and 2 of them are called the type 2A string theory and type 2B string theories, and they look very similar. These are theories. So in string theory, the way the spectrum looks is like, so if you put energies, there's the string scale, and there's like a bunch of states that give you the string scale, and there's a few states here at low energy, the low energy limit. So energy is much smaller than the string scale, that can be described with a Lagrangian and a field theory. Okay, and this theory is a theory of gravity, and it has supersymmetries. It's called supergravity. Now, type 2A and type 2B string theories have a lot of supersymmetry. They have 32 supercharges. And with that much supersymmetry, everything is fixed by supersymmetry. The Lagrangian is fixed by supersymmetry, but also the fields that you have are fixed by supersymmetry. Okay, so the field content is fixed by supersymmetry. The supersymmetries in type 2A and type 2B are slightly different. So the spectrum of type 2A is the metric. A B field. What is a B field? It's a bit like a, the A field of the electromagnetism we're discussing, but with 1 index more. So in the same way, this has a field strength, which is F mu nu. This has a field strength, which is A mu nu rho, has 3 indices. Okay. So it has this thing. It also has 1 scalar, which is the string coupling. It's called the dilaton. And then it has Ramon forms. So they are fields like this. So they're called C mu nu rho blah blah blah, with a number who is completely antisymmetric. And you have P indices, and the number of indices that you have in type 2A, you have different fields. One of them has 1 index, so it's like a vector, it's C1. One has 3 indices, it calls C3. And then, and then there's so there's the C1, C3, and then there's, just like we could do electric magnetic duality for the abelian theory, there's 2 guys. And this guy is electromagnetic dual to this, and this guy is electromagnetic dual to this. And then there's some fermions because of supersymmetry, but we won't care about the fermions. So that's type 2A. Type 2B string theory is similar. It still has a phi and a G and a B, and it also has C mu nu rho in the same, but it has different values of P. So this guy has P equals 0. This is the Ramon axiom I was talking about before, the one which has the shift symmetry. P equals 2, P equals 4, P equals 6, and P equals 8. Okay. So we were just talking about how the Maxwell theory has 1 form symmetry, and we were for instance, construct the charge operator by constructing a Wilson line. But this construction had nothing special about having just one index. You could do Wilson lines like this for the B field, or Wilson lines like these guys for any of the other Ramon fields. So what that means is that these effective field theories that we get at the Lorentz limit of string theory have tons and tons and tons of higher form symmetries. Okay, so this one has a 1-form symmetry, a 3-form symmetry, a 1-form symmetry, 3-form symmetry, 5-form symmetry, and 7-form symmetry. And this one has 0, 2, 4, 6, 8-form symmetries. So type 2A and type 2B are what about P equals 9 in type 2A? Did I forget about that? So let's see. So P equals 9 in type 2A. So, okay. So that would be a space-time. So that would be a C9. Okay. Okay. Yes, that guy is there, but it's a bit different from the others. So I am removing it from the discussion. So to understand why it's different, you must think about something I haven't been describing here, which is how many degrees of freedom have all these higher form fields that I have here. Okay, so a vector, you know, C1, for instance, you know, it has d minus 2 degrees of freedom in the dimension, so it has 8 physical polarizations. This one has some other numbers, so on and so forth. And when you get to the Z9, if you compute how many physical modes it has, it doesn't have any local degrees of freedom. It is a bit, if you're familiar with it, with what happens if you try to study Maxwell theory in 2 dimensions. In Maxwell theory in 2 dimensions, there's no propagating degrees of freedom. Everything is pure gauge. That doesn't mean the theory is trivial, because you can still have fluxes for the gauge field, but there's no local dynamics. So I'm kind of like forgetting a bit about it. Okay, but yeah, sure, we could add it. So let's just put the C9 there. Okay. In fact, I think, sorry, I think for what I'm going to be telling you here, it actually doesn't matter. That is a bit different. So yeah, we should put it there. I guess for other applications, it does matter, and I just tend to omit it by force of habit, but that's a very good point. So you have these guys. So you have all sorts of high form symmetries. So there should be objects that break these high form symmetries. No, that's what we concluded. Well, okay. So let's start with the B field, with these guys. Is there any object that couples electrically to the B field? Okay, and you know, the answer to this question is not obvious from the way that we're presenting it here. But if you're studying string theory and you take a basic string theory course, the first thing you learn about perturbative string theory is that the perturbative string, the fundamental string, couples electrically to the B field. So, yay. If we didn't know string theory and we were just supergravity people and we discovered this Lagrangian because it was very supersymmetric and nice, and we believed there was no global symmetries in quantum gravity, we would be led to conclude there has to be fundamental strings in the theory, just from the completeness principle. But that's not the only thing. The 2-form by electric magnetic duality is related to a potential B6. And the object that couples electrically to this, something like the magnetic monopole, but for the string, is called the NS5 brane. It is an object that we also know exists in type 2B string theory, and type 2A string theory, but we discovered in different ways. And now we know it exists also because of the completeness principle. What about the Ramon guys? All of these guys. Well, for instance, for P1, we need an object. We need a particle, sort of, right? That couples to C1 like a Wilson line, okay? And in general, if you have a P form, you need some object which would have P dimensions of space, okay? So P dimensions of space and 1 of time. sorry, p minus 1. P minus 1 dimensions of space and plus 1 of time. That couples like this. Do those objects exist? Well, you may have heard that in type 2 strings, there's these objects, these extended objects on top of the fundamental string, which are called D-branes. Okay? So in type 2A, there's a D0 brane, which is a particle, a D2 brane, which is a membrane, a D4 brane, D6, and D8. And in type 2B, we have a D1, D3, D5, D7. Okay? And it turns out that each of these branes have the right couplings to break the higher form symmetries of the supergravity. This one couples to this. This one couples to this. This one to this. This one to this. The D8 couples to the P equals 9 case. Okay. Here, there's the P equals 0 case, which is broken by instantonic effects. It's like a zero form symmetry, so it's a bit different than the others. But this one couples to this one couples to this one couples to this, and this one couples to this. So all higher form symmetries in perturbative string theory are broken by non-perturbative effects that you can predict, whose existence you can predict just following the completeness principle. So it's very powerful. Okay. Fine, that's nice, Miguel, you might say. It's very nice that you can predict these branes, but it's also a bit lame that you end up having these things to describe objects whose existence will already existed. So people knew of D-branes and NS5 branes since long ago, since before Swampland. So what is the big idea here? Well, it turns out that yes, these ideas recover everything that was known already, but completeness, they can also be used to predict new branes. Completeness also predicts new branes in string theory. So for instance, there's a paper by Marcus Dierigel, Jonathan Heckman, Ethan Torres, and myself from 21, where we identified some symmetry of the type 2B supergravity. And then we say, well, because of completeness, there has to be a brane that couples to it. And that way we discover a new 7 brane in type 2B string theory. It's called the R7 brane. We check, it passes a bunch of consistency checks. So we really believe it exists. And this brane, it was really predicted from this perspective, not before. Okay. And then there's a very nice set of papers, the last of which I think I have the reference here. Let me just put it. It's a paper by Justin Cady, Yuji Tachikawa, and Yonekura. There's 2 papers. There's one from last year, and just earlier this month they have a longer paper with a lot of details, where they discover new branes in heterotic string theory. Now this paper is super nice because they don't just say, oh, because of completeness principle, the brane has to exist. They say, well, because of the completeness principle, the brane has to exist. And so we should find a perturbative string theory description, a worksheet that describes this brane, and they find it. So they discover a new concrete worksheet CFT that describes the near Harrison geometry of these branes. Okay. So you could say that Swampland was predicting the existence of these CFTs, which were then found in this paper. It's a very interesting story, and it's, you know, cutting edge. This is something that is happening. This paper is from this month, okay? So there's a lot of movement on this area, and there's lots of people who are working to try and use these ideas to predict new objects and to learn about new objects in string theory. So Martí asks why R brain. Babita suggests R equals Ramon. That's not correct. The reason for the R is because it's what we call a reflection brain. Okay. Since you asked, the thing that this brain has, the thing that this brain does, in some ways it behaves as it acts as in some this action. So the brain is related to the action of some symmetry on Ramon fields of type 2B string theory, which flips their signs. It's a bit like charge conjugation. It's a bit like a reflection on a mirror. And the symmetry that that one is using to construct this brain is a symmetry that has to do with some sort of reflection of some auxiliary space that one has in type 2B string theory. So in what is called the F theory description, this brain implements a monodromy of a reflection of the F theory torus, if that says anything. So that's why it's called the reflection 7 brain. Okay, very good. So yeah, completeness is cool. It predicts new objects. So the one lesson that one can draw from this is that what is the name of the brains in the second paper? So in the second paper, they have they just don't have one. They have like 4 new brains. Okay. So I don't think they give them names. They just describe what they are, and there's like they tell you what they are. So like the brain that does this, the brain that does that. But I don't think they put names to them, which is a missed opportunity. It's very fun to put names on things. But I don't think they put a name on it. One of the brains that described in this paper was already predicted some years ago by different arguments from Polchinski. So sometimes people call it the Polchinski zero brain, but you know, there's no descriptive name of the brain. Very good. So yeah, so what we learn from this is that, you know, no global symmetry is maybe not so helpful at zero form symmetry level. Just tells you that some symmetries are broken by some effects. But completeness principle, so no global symmetries for high form symmetries, lets you get a lot more. So completeness, so completeness principle tells you, the basic lesson is that we can learn a lot, not just from the presence of symmetries. Learning a lot from the presence of symmetries is what one does in quantum field theory. If you have a quantum field theory and you have a global symmetry, you're happy. You have a lot more control of the theory because you can use the symmetry to constrain the dynamics. In quantum gravity, we do the opposite. We can learn a lot not just from the presence of the symmetries, but from the fact that they're broken, from their absence. And so this leads to an algorithm for people working on Swampland program, which is look for symmetries, look for the effects that break them, okay? And use that to make predictions, okay? So now I'm gonna give you a concrete example. I'm gonna give you something which is called the tip of the iceberg of a bunch of developments that have been happening over the past few years of using the completeness principle combined with some techniques called anomaly inflow to try and rule out effective field theories. Okay? So what have we done so far is we've concluded, okay, if you have a theory with Maxwell, it must have monopoles. If you have a theory with Ramon fields, it must have D brains. That's interesting, but can we use this to rule out some effective field theories? And the answer is yes. Okay? So let's see how can these ideas can be used to rule out theories. And I'm just going to give you one example of actually the first example of this set of ideas, but it doesn't have to. You know, there's many more. Okay, so this is a paper 1905.08261 by Kim, Xiu, and Kurumbafa, where they use these ideas to solve to attack a problem from Swampland point of view. That is quite important. So they use this theories to constrain the landscape of 6D theories of gravity and also 10D theories. Now, I am going to be describing the case of 10D theories because it's simple and nice, but I would say the more interesting application of the results is in 6 dimensions. So let me explain that. So they use the completeness principle to constrain theories in 10 dimensions with n equals 1 supersymmetry in 10 dimensions. Okay? So what does that mean? Well, the theories that we are describing here, these type 2 string theories, have 32 supercharges that's n equals to 2 in 10 dimensions. The theories they constrain, they have 16 supercharges in 10 dimensions. Okay? And so with 16 supercharges, the dynamics of the theory is very constrained by SUSY. It's very much constrained by supersymmetry. So, so the dynamics is very much constrained by supersymmetry. And the only data that is left unspecified is the choice of gauge group G. So in these theories with 16 supercharges, in 10 dimensions, you still get to choose the gauge group of the theory. So it could be U1, it could be SU2, it could be, yeah, in principle, you can pick whatever you like. So you need to pick some gauge group G. However, in 10 dimensions, there are constraints, not from string theory, constraints from one loop calculations, which are commonly referred to as anomalies, that put restrictions to G. So if you do the theory classically, you could get any G that you like. But if you take into account these constraints, these quantum consistency constraints, which are called anomalies, they're very rigorous. You can learn about anomalies in these theories in the Green, Schwarz, Witten textbook. Okay. So there's a textbook. So this is in the volume 2. So the first textbook on string theory. So you look at volume 2. So they discuss this. And so if you take into account the constraints from anomalies, there turns out to be that not every G is possible. There are just 4 possibilities. And that's gauge group E8 cross E8, gauge group SO32, gauge group U1 to the 248, and gauge group, times E8, and gauge group U1 to the 496. These are the 4 possibilities. Okay? And then you could ask, okay, fine. So this is all using effective field theory. I haven't imposed any quantum gravity consistency. Maybe I can get all of them in string theory? And the answer is you cannot. So this one, and this one, we know how to get in string theory. They are the low energy limits of the 2 heterotic string theories in 10 dimensions. But this one and this one, nobody knows how to get from string theory. Okay. There's no way to get them from string theory, even though they're completely consistent as field theory solutions. They satisfy all the constraints they need to satisfy. So there was an argument in a 2010 paper. Oh, sorry. No, there's a 2010 paper by I think I have the so it's by Watty Taylor and the Wolf and friends, where they argue that just from supersymmetry, then by looking at some careful conditions, then the last two are not possible. But Kim, Xiu, and Baffa, in this 1919 paper, they got it from a Swampland argument. They say, all these theories have a B field. So this just follows from supersymmetry. So there is a fundamental string by the completeness principle. And they assume that the string is BPS. And if you assume that the string is BPS, you can constrain its dynamics. And by studying the effective field theory, on strings, they find is on the effective field theory on the strings is only consistent. So this is not the effective field theory of spacetime, it's just imagine a one long string and they study the world volume theory of the string that gets you what is low energy dynamics. So they find that this is only consistent for the OK theories. So not for the other ones. Okay, so they show that everything you can get from string theory is actually the things that are compatible with Swampland principles. You might say, oh, but these people already knew that. But the thing is that then they now produce constraints. This is why I said in 6 dimensions is more interesting. They produce constraints in 6 dimensions, ruling out many families of theories. That don't have a string embedding. So they're ruling out theories. For instance, in 6 dimensions, a theory with gauge group E8 times E8 times E8, like a very large bunch of E8s, they show it's in the Swampland. This is an example of a constraint they have. Okay, so now, and the way they do it is they show that such a theory would have strings and the strings would be inconsistent. So the mere fact that you have completeness principle and you have these extended objects, because the extended objects have to be consistent, can be leveraged to constrain the physics at very low energies. Okay, so it's an example of how the Swampland ideas, in an indirect way, can produce. So Swampland ideas. Okay, let me just. So Swampland ideas can produce very strong constraints at low energies. So this paper has had a lot of following. There's been a lot of papers following on variations of these ideas. Sometimes you construct objects which are related to non-trivial topology of spacetime. So that goes under the name of covariance conjecture. So covariance conjecture is completeness for gravitational symmetries. I mean, I am not telling you exactly what all of these words means. I just want you to know that if you ever see in the literature the words covariance conjecture, you should know it's in the ballpark of ideas of the completeness principle. Okay, So there's lots of papers that have been constraining theories, particularly supersymmetric theories. And for instance, now we have achieved in 9, 8, and 7 dimensions with theories with 16 supercharges. Sorry, in 10, 9, and 8 dimensions, we have achieved in 10, 9, 8 dimensions with 16 supercharges, we have achieved string universality, what we call string universality. Which means everything that is consistent with Swampland can be realized in string theory, and everything inconsistent cannot. So it's like you have effectively theories can be coupled to gravity. There's the ones that you can get from string theory, and there are the ones that that are constrained by Swampland. And these two are exactly the same set of theories. So it's not that one contains the other, the two are exactly the same. So with this, I finished what I wanted to tell you about things related to the no global symmetries conjecture. It's a very in a sense it's really fascinating that just general principle about quantum gravity, when you start following its thread, can lead you to constraints on large and effective theories. And there's a lot of people working on this right now. For the last lecture, we'll focus mostly on the weak gravity conjecture and a little bit of the distance conjecture, which are the two other important Swampland constraints. But I wanted to focus and give a lot of reviews on these ideas, which are related to no global symmetries, because they have been one of the recent angles of the Swampland program that has exploded. And they are the set of ideas which is most closely related out of all the Swampland program to black hole physics, which was part of the point of the course. So with this, I finish. Sorry if this last part, I was not asking for questions as much, because I wanted to be done with the global symmetries for today. But now we are done with the lecture. Thanks so much for listening, and I'm happy to take any questions you may have.